Welcome to reading number 11 of History, Fiction, or Science by Anatoly Fomenko. We are starting in Chapter 2, Astronomical Datings, and not really a review, but a recap of Chapter 1 was basically laying a whole lot of groundwork in multiple disciplines and sciences, discussing at length the chronology of Scaliger Batavia and how all the holes in that chronology, all the holes in their geography and biblical geography, dendrochronology, just a massive amount of various facets to whether or not what we've been told about history is true. So we are going to pick up here in Chapter 2, Astronomical Datings. Now, I'm fully confident that both those who come from the perspective of living on a plane and a planet can appreciate what is being said here, since you don't really have to be confident of either one that you're living on to appreciate the movements in the heavens. So Section 1 of Chapter 2, Astronomical Datings, is the strange leap of parameter d in the theory of lunar motion, and this was covered briefly in the introduction and Chapter 1. Nowadays, we have special calculation tables, the so-called canons, whose compilation was based on the theory of lunar motion. They contain the date of each eclipse, the area to be covered by the lunar shadow, the phase, etc. See the famous astronomical canon of Genzel, for instance. If an ancient text describes some eclipse in enough detail, we can determine what characteristics of the eclipse had been observed, the phase, the geographical area that the shadow passes over, etc. The comparison of these characteristics to the referential ones contained in the tables may give a concurrence with an eclipse possessing similar characteristics. If this proves a success, we can date the eclipse. However, it may turn out that several eclipses from the astronomical canon fit the description. In this case, the dating is uncertain. All the eclipses described in the ancient and medieval sources have been dated by the following method, to some extent at least. And then he gives 6 different bibliographical references. Nowadays, the dating of the ancient eclipses are occasionally used in astronomical research. For instance, the theory of lunar motion has the notion of the so-called parameter d, the second derivative of lunar elongation that characterizes acceleration. Let us remind the reader of the definition of elongation. Figure 2.1 shows the solar orbit of the Earth and the telluric orbit of the Moon. The angle between the vectors ES and EM is called lunar elongation d, the angle between the lines of sight drawn from the Earth to the Sun and the Moon. Apparently, it is time-dependent. An example of the elongation of Venus can be seen in the picture on the right. Maximal elongation is the angle where the line of sight is drawn from Earth to Venus, touches the orbit of Venus. One has to note that the orbits in figures 2.1 are shown as circular, while being elliptic in reality. However, since the eccentricity is low here, the ellipses are schematically drawn in circles. Some computational problems related to astronomy require the knowledge of lunar acceleration, as it had been in the past. The problem of calculating parameter d over a large time interval as a time function was discussed by the Royal Society of London and the British Academy of Sciences in 1972. The calculation of parameter d was based on the following scheme. The equation parameters of lunar motion, including d, are taken with their modern values and then varied in such a way that the theoretically calculated characteristics of ancient eclipses coincide with the ones given for dated eclipses in ancient documents. Parameter d is ignored for the calculation of actual eclipse dates, since the latter are a rougher parameter whose calculation does not require the exact knowledge of lunar acceleration. Alterations in lunar acceleration affect secondary characteristics of the eclipse, such as the shadow track left by the moon on the surface of the Earth, which may be moved sideways a little. The time dependence of d was first calculated by the eminent American astronomer Robert Newton. According to him, parameter d can be defined well by the abundant information about the dates scattered over the interval from 700 BC until the present day. Newton calculated 12 possible values of parameter d, having based them on 370 ancient eclipse descriptions. Since our Newton trusted Scaligean chronology completely, it is little wonder that he took the eclipse dates from Scaligean chronological tables. The results of R. Newton combined with the results obtained by Martin, who was processed about 2,000 telescopic observation of the moon from the period of 1627 through 1860, 26 values altogether. I believe he meant to write who has processed, have made it possible to draw an experimental time dependency curve for d, and that's shown in figure 2.2. So the first two graphs on this page here, I'm floating my mouse over the one for the moon. The second one he's showing for Venus, these parameter graphs that they can make. And then the third one here on the right page. According to R. Newton, the most stunning fact is the drastic drop in d that begins with 700 AD and continues until about 1300. This drop implies the existence of a square wave in the oscillating value of d. Such changes in the behavior of d and such rates of these changes cannot be explained by modern geophysical theories. Robert Newton wrote an entire monograph titled Astronomical Evidence Concerning Non-Gravitational Forces in the Earth-Moon System that was concerned with trying to prove this mysterious gap in the behavior of d, which manifested as a leap by an entire numeric order. One has to note that these mysterious non-gravitational forces failed to manifest in any other way at all. Having studied the graph that was shown as a result of these calculations, R. Newton had to make that, in quotes, between the years -700 and +500, the value of d remains the lowest as compared to the ones that have been observed for any other moment during the last 1,000 years. Newton proceeded to tell us that, quote, these estimations combined with modern data tell one that d may possess amazingly large values, and that it has been subject to drastic and sudden fluctuations over the last 2,000 years, to such an extent that its value became inverted around 800 AD. Summary. 1. The d value drops suddenly, and this leap by an entire order begins in the alleged 5th century AD. 2. Beginning with the 11th century and on, the values of parameter d become more or less constant and close to its modern value. 3. In the interval between the alleged 5th and 11th centuries AD, one finds d values to be in complete disarray. The strange fact has a natural explanation within the paradigm of new chronology. Section 2. Are the ancient and medieval eclipses dated correctly? 2.1. Some astronomical data. Let us give a brief digest of the information that shall ensure a better understanding of the current chapter. More detail can be found in such sources as, and he gives bibliographical source 534, for instance. When the moon gets into the cone of telluric shadow, one can observe a lunar eclipse on Earth, more specifically, on its nocturnal hemisphere, the one that faces the moon. A lunar eclipse can be observed from any point of the Earth's nocturnal hemisphere. An eclipse doesn't last longer than 3 hours and is only possible during a full moon. However, due to the irregularity of lunar motion, it doesn't happen every time the moon is full. The repetition of lunar eclipses is roughly and approximately periodic and conforms to the so-called Saros cycle. A Saros period equals about 18 years. 28 lunar eclipses occur over this time, and so on, so one can find an eclipse that falls over virtually every given year. A Saros is easily determined over 50 to 60 years of systematic observation, and might have already been known at the dawn of astronomy. The prediction of lunar eclipses based on the Saros cycle is nevertheless somewhat uncertain, not only due to the imprecision of the Saros cycle, but also because of the fact that the eclipse might occur when the hemisphere where the observer is located is illuminated by sunlight, which renders the moon invisible. A solar eclipse occurs when the observer gets into the cone of the lunar shadow. If the solar disk is completely covered by the moon, the place where the eclipse can be observed becomes darkened to the extent of making the stars visible. This is a full eclipse whose duration does not exceed 8 minutes in the equatorial zone and 6 in modern latitudes. The lunar shadow moves across the surface of the Earth at a speed of about 110 meters per second, forming a narrow line. The width of this line does not exceed 4 degrees. The track of the umbral shadow is bordered by stripes of penumbral shadow, whose width as counted from the center of the umbral shadow comprises about 30 degrees in moderate latitudes and about 15 degrees near the equator. The observer in the penumbral shadow only sees a partial covering of the solar disk by the moon, a partial eclipse. The maximal degree of the covering of the solar disk by the lunar shadow is called the depth, or the phase of the eclipse. The estimations of the phase are usually expressed by the B value that is calculated by the formula B equals 12H, H being the ratio between the shadow-covered part of the solar diameter and the entirety of the latter. Hence, a total eclipse of the sun will have a phase value of 12. A solar eclipse becomes visible as a darkening of the solar disk, starting with the phase values of 3 inches to or minus 4 inches. The lunar eclipse phases are calculated differently, namely, another item that is proportional to the duration of the eclipse, if the latter is more than full, is added to the phase value of 12 inches. Thus, the phase value of lunar eclipse might reach up to 22.7 inches. And I have to say inches because it is a double apostrophe, which I would read as inches as a carpenter. In cases of solar eclipses, there may be situations when the cone of the moon's umbral shadow does not reach the Earth. In this case, an annular solar eclipse is possible when no stars are visible, as in the case with all partial solar eclipses. A solar eclipse is only possible when the moon is new. However, not every new moon is marked by a solar eclipse, since the Earth may slip past the cone of the lunar shadow due to the incline of the lunar orbit towards the ecliptic, or the plane of the telluric orbit. This is why there are only 2 to 7 solar eclipses happening every year. Every geographical area of the Earth gets an eclipse with a minimal phase value of 6 inches in the span of 10 to 20 years from any date. Predicting solar eclipses is a truly formidable task due to the complexity of the lunar motion that is defined by a large number of external forces. One may attempt to predict solar eclipses by the Saros cycle that includes about 43 solar eclipses, 15 of them being partial, 14 annular, 2 belonging to the category of the so-called total annular, and 12 total. However, the eclipses from the Saros cycle can occur in different areas of the Earth, and so a prediction for a given location is true in one case out of 400 in general. That is to say, the probability of a correct prediction based on the Saros cycle equals 1 in 400. In theory, the so-called triple Saros, whose duration is 24 years, should be more precise. However, the probability that it may give a correct prediction equals about 1 in 99, so it is of little practical utility. From the astronomical point of view, the empirical triple Saros can only be discovered as a result of long-time solar eclipse observations, due to the low recurrent rate of eclipses separated by the triple Saros, let alone the problems of mathematical processing of the empirical data necessary for the calculation of an undefined recurrence rate, and such discovery would imply a well-developed system of natural science. A more or less certain prediction of solar eclipses is apparently only made possible by the existence of a sufficiently advanced theory of lunar motion that would at least account for the principal irregularities of the latter. Thus, the prediction of solar eclipses remained a de facto impossibility 100 years after Copernicus. We should thus treat the eclipse prediction reports preceding the 16th and 17th centuries with the utmost caution, or even suspicion. And I just really want to point out, before we go on to section 2.2, that no one has actually recorded the moon in the sky converging on the sun during a solar eclipse. I mean, you can say all you want that you see something circular covering the sun, and I agree, but no one's actually ever recorded the moon. It's just an assumption that it is a moon in new phase. Now, I'm not going to argue about what it is, but let's just be honest and say that no one's ever actually seen the moon in the sky. They cannot record it in the sky. They've tried to. Anyways, so a lot of this, the dialogue and these terms he's using, I'm not pretending that I'm utterly familiar with all of them, you know? Like, I don't know, the triple Saros. I heard that dive was impossible. Or maybe I'm thinking of the triple Lindy. Either way, on to section 2.2, the discovery of an interesting effect, an unprejudiced astronomical dating shifts the date of the ancient eclipses to the Middle Ages. Ooh. Dealing with certain celestial mechanics issues in the 1970s, the author of the current book, that's this one, discovered the possibility of a link between the alleged gap in the value of D and the results of N.A. Morozov's research concerning the datings of ancient eclipses. A study of the issue and a new calculation of parameter D attains an altogether different quality, namely, one sees the complete elimination of the mysterious leap. Parameter D appears to be subject to minute fluctuations around one permanent value coinciding with the current value of this parameter, and he gives bibliographical articles. All of this can be summed up as follows. The previous calculation of parameter D was based on the dates of ancient eclipses used in the consensual chronology of Scaliger-Petavius. All the astronomers' attempts to explain the strange gap in D didn't get anywhere near the issue of the correctness of datings considered ancient and early medieval nowadays. In other words, in how far the parameters of the eclipse described in the chronicle correspond with the calculated parameters of the real eclipse that Scaliger chronology suggests to be described in the chronicle in question. The following method of independent astronomical dating was proposed in, and then bibliographical reference 544. Obtaining all of the characteristics described in the chronicle, such as the phase, the time, geographical observation, location, etc., and copying all of the eclipse dates fitting these characteristics from the reference tables mechanically, N.A. Morozov described that the astronomers have been under the pressure of Scaligerian chronology, and so only considered the dates that Scaligerian chronology had already ascribed to the eclipse in question and the events related thereto. As a result, in many cases, astronomers failed to find eclipses corresponding to the chronicle description in the required century, and had to resort to approximations without the merest thought of questioning Scaligerian chronology and indicating eclipses that would fit the chronicle description partially. Having revised the datings of the eclipses considered ancient, Morozov found that the reports of these events fall into two categories. 1. Brief and nebulous accounts with no details given. In many cases, it is altogether unclear whether the event described is an eclipse at all. The astronomical dating in this category either has no meaning whatsoever or gives so many possible solutions that they can basically fit any historical epoch at all. 2. Exhaustive detailed reports. The astronomical solution for those is often singular, or there are 2 or 3 solutions at most. Apparently, all of the eclipses with detailed descriptions falling into the period between 1000 BC and 500 AD get independent astronomical datings that differ significantly from the ones offered by Scaligerian chronology and belong to a much later epoch, namely the interval between 500 and 1700 AD. Being of the opinion that Scaligerian chronology was correct about the interval 500 to 1800 AD for the most part, Morozov did not analyze the medieval eclipses of the 500 to 1700 AD, assuming that no contradictions would be found there. Let us dwell on this for a short while. Morozov didn't possess the sheer deliberation needed for the realization that Scaligerian chronology had been erroneous up until the epoch of the 11th to 13th century AD. He stopped with the 6th century AD, assuming more recent chronology to be correct in the form offered by Scaliger and Petavius. His erroneous presupposition naturally affected the analysis of the ancient eclipses. We see today that Morozov's analysis was not completely objective. since he had obviously been reluctant to alter the post-6th century chronology. This isn't hard to understand, as the transition from the artificially extended Scaligeриan chronology spanning millennia to a much shorter one beginning with the 11th century AD looked absurd even to N.A. Morozov. In Volume 4 of 544, for instance, Morozov discusses one of the eclipses that is today ascribed to the 5th century AD, being of the opinion that its Scaligeриan dating is confirmed. However, it becomes obvious that no confirmation of the Scaligeриan chronology could have possibly taken place. The description of the eclipse is quite nebulous, and the use of comets for dating purposes is impossible due to reasons that shall be related in the chapter of Chronology 5, where we consider comet lists specifically. Being certain that Scaligeриan history was following the correct chronology ever since the 5th century AD, Morozov was inconsistent in his analysis of post-5th century eclipses. Had he encountered an equally nebulous description referring to a pre-4th century eclipse, he would have just considered it a description that cannot be proved astronomically. Morozov made a similar mistake in his description of other eclipses dated to the alleged 5th through 6th century AD. He treated them a lot more benevolently than their pre-4th century precursors. The eclipses of the 6th through 11th century weren't checked by Morozov at all, since he had believed the Scaligeриan datings to have been satisfactory. Unlike Morozov, we have continued with the critical research, having covered the post-5th century period up until the 17th century AD, and discovered that Morozov should not have stopped with the 4th and 5th century. The datings of the eclipse descriptions that are ascribed nowadays to the 10th through 13th century AD contradict astronomy to just as great an extent as those preceding the 4th century AD. In cases when there is a concurrence of sorts, one almost always discovers that these eclipses have been calculated a posteriori, that is, affixed to a certain point in the past by the medieval chronologers of the 16th and 17th century, in order to confirm Scaligeриan chronology, whose naissance occurred around that time. Having calculated the dates for certain lunar eclipses of the past, Scaligerite chronologers included them in the ancient chronicles that they were creating in order to give, in quotes, solid proof to the false chronology. It is, of course, possible that the odd occasional veracious description of the 6th through 13th century eclipses would reach the chronologists of the 16th and 17th century. However, it would surely have to pass the filter of the Scaligeриan version and be, quote, brought into accordance, unquote, with the, in quotes again, correct dates. Thus, continuing the research that began in, and he lists 544 again, the bibliographical, and I believe, I'm sorry, I just want to make absolutely sure about this. Well, that's 534 is Newton's paper, so 544. If you flip back in here, the digital copy I have on the screen, you actually ought to be able to find the bibliographical references. Anyways, way too many of them for me to go to them and cite them every time. Anyways, thus continuing the research that began in 544, the author of this book conducted an analysis of other medieval eclipses in the interval between 400 and 1600 AD. It turned out that the transfer effect affecting the ancient eclipses as described in 544 also applies to those usually dated to 400 to 900 AD, also applies to those usually dated to 400. I'm sorry, I just read that twice. I guess I got lost in the page. I'm sorry. He's saying the ancient eclipses as described in 544 also applies to those usually dated to 400 to 900 AD. This either means that there are many possible astronomical solutions which make the dating uncertain, or there are just one or two, in which case they all fall in the interval between 900 and 1700 AD, only starting with approximately 1000 AD and not 400 AD, according to Morozov in 544. So that reference is from Morozov. Does the Scaligean dating begin to concur with the results of Morozov's method satisfactorily enough, becoming more or less certain by as late as a date of 1300 AD? Let us give a few extremely representative examples demonstrating how the ancient eclipses and the chronicles that describe them become a great deal younger. And by the way, I did a relatively exhaustive search trying to find the writings of N.A. Morozov translated into English, specifically his work Christ, which is referred to frequently by Fomenko up to this point, and I cannot find any of it thus far translated into English. So it's just another one of those factors that should be cataloged. When anyone's thinking if this is some grand psyop, it seems that Morozov's work is possibly the greatest basis of a lot of Fomenko's work, and yet no one has really paid it enough attention to even fully translate it and make it available in English. Section 2.3. 3 eclipses described by the ancient Thucydides. Scaligean history tries to convince us that Thucydides was born in approximately 460 BC, or 456 to 451 BC, and died around 396 BC. He was a wealthy aristocrat and politician from Athens. During the Peloponnesian War, Thucydides was in command of the Athenian fleet, albeit unsuccessfully. He was subsequently banished from Athens for 20 years. He wrote his famous tractate during his sojourn in Thracia. Thucydides had received amnesty near the end of the war. He returned to Athens and died shortly afterwards. Historical tradition trusts Thucydides in his descriptions of military events, considering him an eyewitness and a participant. Thucydides himself writes the following: I was writing down the events witnessed by myself as well as what I had heard from others, after as meticulous a study of each fact as circumstances allowed. I have survived the entire war, understood it, and studied it attentively. Thucydides is the only source that we have in what concerns the history of the Peloponnesian War. Historians write that after Thucydides, nobody turned to the history of the Peloponnesian War ever again. Many have, however, thought it would prove flattering for them to be seen as his followers, and started their own works where the tractate of Thucydides ended. It is supposed that the work of Thucydides either hadn't had any title at all originally, or had been called Communal Account in Greek, having received the name History of the Peloponnesian War in later translations. The entire historical account of the 27-year war between the Ionians and the Dorians — could Doria mean horde when read in reverse? — is given by Thucydides clearly and consequentially, though it remains incomplete. The entire work of Thucydides, whose volume comprises about 800 pages when printed, is written in a brilliant style, Numerous commentators have pointed out the following hallmarks of his book a long time ago. 1. Thucydides demonstrates great erudition and writing experience. 2. The phrase constructions are complex and contain non-trivial grammatical structures. 3. One sees a clear development of an elegant, realistic concept in the account of historical facts. And 4. The author is skeptical about everything supernatural in people's lives. We are being convinced that this work was written in the 5th century BC, when writing materials had still been scarce and expensive, they say. The Mesopotamians use styluses to scribble on clay. The Greeks aren't familiar with paper yet and write on pieces of tree bark or use sticks for writing on wax-covered plaques. Give me a break. The oldest written copy of the history of Thucydides is supposed to be the Codex Laurentinianus. Yeah, it's a long one. The Codex Laurentinianus parchment dated to the alleged 10th century. All other old manuscripts belong to the alleged 11th and 12th centuries. Some papyrus fragments of the second book of Thucydides were found in, of all places, Egypt, in the 14th century. That's a pregnant pause for reflection. A papyrus commentary is also in existence, published as late as 1908. However, the condition of these fragments is very poor indeed. Let us note straight away that the datings of all the oldest manuscripts listed are based on paleographical hypothesis exclusively, and therefore don't seem trustworthy. Any alteration of the chronology changes all of these paleographical datings automatically. That's pretty heavy, Doc. There are no calendar dates mentioned in the History by Thucydides and no planetary horoscopes. However, it contains the description of 3 eclipses. 2 of them are solar, 1 lunar. We shall be calling this combination as a triad. Apart from that, the first book contains mentions of solar eclipses. However, those are rather general and vague, and cannot serve for any astronomical dating. The descriptions of the triad, however, are quite sufficient for an unambiguous solution. We shall consider it below. The second volume of history contains a rather detailed description of the eclipse. In parentheses, the Russian original refers to the well-known professional Russian translation of Thucydides done by F.G. Mishenko in the 14th century. Thucydides writes that, quote, "The summer when the Athenians have chased the Aegineans with their wives and children from Aegina." Thucydides is referring to the first year of the war. "The very same summer, when the moon was new, apparently that is the only time when such things can happen. The sun became darkened after midday and became full again, attaining the shape of a crescent, and several stars appeared. The Greek text can be seen in figure 2.3. Let us pay attention to the fact that the author appears to understand the mechanism of the eclipse well, mentioning the new moon to be a necessary condition, which is a reference to a long-time practice of eclipse observation in the epoch of Thucydides." Then he actually gives the Greek, and I believe each one is a transcription, figures 2, 3, and 2.24. In figures 2.3, the Greek text of Thucydides describing the first eclipse from the Thucydides Triad, taken from page 176, and the second is the same from Thucydides describing the second eclipse from the Thucydides Triad. Okay, the second eclipse of the Triad, also solar, happens in the 8th year of the Peloponnesian War, in the beginning of summer. Thucydides writes in the fourth... Man, I wish it was the beginning of summer. I'm serious. Anyways, Thucydides writes in the 4th volume that, quote, "The winter has ended, and with it the 7th year of this war, whose history has been described by Thucydides. In the beginning of the next summer, with the advent of the new moon, a partial solar eclipse took place." The Greek text can be seen in figure 2.4. Apparently the summer month mentioned as the month when the estival campaign began was March, the month of Mars, when military campaigns were usually started. It shall be interesting to verify this statement after the finite solution of the problem is obtained. The third lunar eclipse is described in the 7th volume. Quote, "The winter was coming to an end together with the 18th year of the war, whose history has been described by Thucydides. As soon as the next spring began, the Lacedaemonians and their allies invaded Attica in the earliest season. The events of the summer are related in detail further on. The analysis of the maneuvers described shows that the next sections most probably refer to the end of summer. This is where Thucydides writes that, quote, "When everything was ready and the Athenians were prepared to sail away, a lunar eclipse occurred. It had been full moon then." Let us sum up. The following information can be obtained from the text by Thucydides with absolute certainty. 1. All 3 eclipses were observed from the square fitting into the following geographical coordinates: longitude between 15 and 30 degrees, latitude between 30 and 42 degrees. The first eclipse is solar. The second eclipse is solar. The third eclipse is lunar. The time interval between the first 2 eclipses equals 7 years. 6. He's giving points, and I'm not reading the points. Sorry. The interval between the second eclipse and the third equals 11 years. The first eclipse occurs in the summer. The first solar eclipse is a total eclipse, since one can see the stars. That is, its phase value equals 12. Remember, one cannot see any stars during a partial eclipse. The first solar eclipse occurs after midday local time. The second solar eclipse occurs in the beginning of summer. The lunar eclipse takes place around the end of summer. The second solar eclipse occurred within the temporal vicinity of March. As a matter of fact, this consideration doesn't have to be included in this list. The problem can be formulated as follows: finding the astronomical solution that would satisfy the requirements of 1 through 11. Historians and chronologists have naturally paid attention to such a precise description of 3 eclipses in an ancient work, and tried to date them accordingly. Apparently, the chronologists immediately ran into serious difficulties that haven't been overcome since. We shall proceed to give a more detailed account of the problem of dating the Triad of Thucydides, following the well-known astronomical work of Ginzel. In the 16th century, the chronologer Dionysius Petavius found the date. I'm just ha-ing because he's called a chronologer. Dionysius Petavius found the date that fitted the first eclipse, 3rd of August, 431 BC. Johannes Kepler later confirmed the fact that there was indeed an eclipse that day. The beginning of the Peloponnesian War was dated to the very same year, 431 BC. Petavius found the dating of the second eclipse as well, which was 21 March 424 BC. J. Kepler also confirmed the fact that a solar eclipse took place that day. The date that D. Petavius found for the third eclipse was 27 August 413 BC. This is how astronomy appears to have dated the events described by Thucydides to the 5th century BC. However, a secondary analysis of the astronomical solution offered by Petavius unearthed serious complications that were repeatedly discussed in astronomical and chronological literature in the 18th through 20th century. These rather heated debates have recurred and abated several times. However, modern historians prefer to remain taciturn in everything that concerns this long and difficult discussion, pretending that the problem doesn't exist and has never existed. The main dating problem that the chronologers ran into concerned the first eclipse. The fact of the matter is that the eclipse of 3 August in 431 BC proved an annular one, and so it couldn't have been total anywhere on Earth. This was realized after the inclusion of the Scaliger's astronomical dating of the beginning of the Peloponnesian War into Scaliger's chronological tables. This eclipse is claimed to have been annular by Genzel's canon as well. The fact that the eclipse in question was an annular one can also be proved by the existing computer software for eclipse calculations. We have verified it using a simple program called TurboSky that was developed by the Muscovite astronomer A. Volinkin, not Abe Lincoln, A. Volinkin, in 1995, which is easy to use and convenient for approximate calculations. The eclipse of 3 August that occurred in 431 BC was in fact an annular eclipse. However, Thucydides tells us explicitly that stars were visible during the eclipse. As we have already stated, one cannot observe the stars during a partial eclipse. Furthermore, it turned out that the phase values of the Petavius eclipse of 431 BC was rather small in Athens, which means Kepler has also made a mistake in his optics, telling that the phase value of this eclipse had equaled 12, or, in other words, that the eclipse had been total. Such a statement on the part of Kepler is most probably explained by the imperfection of the eclipse calculation methods of his age. The calculation of the phase of an eclipse is a delicate matter. However, we should not exclude the possibility that Kepler, who was involved in many chronological matters, had been perfectly aware of the fact that one can only see the stars during a total eclipse, and slyly transformed the annular eclipse of 431 BC into a full eclipse in order to make it satisfy the description given by Thucydides and protect the nascent Scaliger's chronology from such an unpleasant dissonance. Kepler had been in constant contact with Scaliger, who had been his correspondent. Soak that one in for a minute. Now, who out there is familiar with the very peculiar and shady history of Johannes Kepler and Tycho Brahe? Because it is believed by many that Kepler may have, at worst, poisoned Brahe and stolen all of his work, because Kepler was not nearly the mathematician and astronomer that Brahe was. And at best, he definitely, from all aggravating and mitigating factors, he did probably at least plagiarize the crap out of Brahe. And it would appear that if he was if he was a close correspondent with Scaliger, that's strikes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Not a good rap sheet, I'm saying. Due to the above-mentioned circumstances, astronomers and chronologists, and you do have to look at somebody's character when you're considering the information that they have presented. Always. You don't get to compartmentalize those things. Due to the above-mentioned circumstances, astronomers and chronologists started new calculations of the phase of the eclipse that took place in 431 BC. All sorts of empirical corrections were made in the equations of lunar movement in order to make the phase value of the eclipse as observed from Athens and neighboring areas approach 12. Among the most prominent astronomers of the time that have dealt with the Thucydides triad problem, we find such names as Petavius, Zech, Heiss, Struck, Kepler, Riccioli, Hoffman, Ginzel, Johnson, Lynn, Stockwell, and Seyfarth. According to Petavius, the phase value of the eclipse equaled 10, and then there's, of course, the inch mark, and then 25. I'm not familiar with that particular phasing numerical representative. The phase value equaled 11 inches according to, and it must be, I'm sorry, it can't be degrees. He's not using a degree sign, and I keep thinking it should be like degrees. I'm going to keep saying inches just because it's a double apostrophe here. So I apologize if I'm completely botching that, but that's basically what is on the page. The phase value equaled 11 inch according to Struck, and then 10 inch mark 38 according to Zech, 10 inch mark 72 according to Hoffman, and only 7 inch mark 9 according to Heiss, with an exclamation point from Fomenko. Ginzel devoted the most attention to the problem of the stars of Thucydides. He came up with a phase value of 10. It became perfectly clear that apart from having been annular, the eclipse could only have been observed from Athens as partial, and with a rather small phase value at that. The lunar shadow track on the surface of the Earth during the eclipse of 3 August 431 BC is shown in Figure 2.6 as a dotted line, which signifies the fact that the eclipse was an annular one. No umbral shadow could be observed anywhere. The fact that the phase value of the Athenian eclipse of 431 BC only equaled 10 means that 1/6 of the solar disk was open. This is all but bright daytime, and one naturally cannot see any stars or planets. Furthermore, it is made obvious in Figure 2.6 this eclipse had only passed Crimea around 1722 local time, or 5:22 p.m. Thus it can hardly be called an afternoon eclipse, as Thucydides explicitly states. It should rather be called an evening eclipse. I'm going to go to that graphic. It's right here. So he showed, I'm sorry, yeah, he showed what's supposed to be the triad map here on the page before concerning these eclipses. Yeah, then he's giving a graphic as far as how much of the sun would have actually been covered for that kind of eclipse. I've been in eclipses like this, where basically it's like just over half coverage of the sun, and it's essentially almost like a kind of a cloudy day. You're not going to see stars. Absolutely not. Okay, we have computed the respective positions of the moon and the sun at the moment when the phase value had been maximal for the observation point, the city of Athens and the area around it. One can see the screenshot in Figure 2.7. it's obvious that a large part of the solar disk is open and neither stars nor planets can possibly be seen. Planets, also known as wandering stars, because of their retrograde motion. Thus, the eclipse of the 3rd of August, 431 BC couldn't have been the one described by Thucydides, since conditions 8 and 9 aren't satisfied as shown above. This discovery was naturally a most unpleasant one for the Scaligerite chronologers and historians. The astronomer Genzel went so far as to claim that, quote, the low phase value, which equaled 10 for Athens according to the latest calculation, caused a shock and significant doubt about the fact that, quote, the stars could be seen, as Thucydides claims, unquote. Since the stars clearly couldn't have been visible during the eclipse of 431 BC, Heiss and Lin decided to calculate the disposition of bright planets in hopes that they might save the situation. However, it turned out that Mars was only 3 degrees above the horizon. Venus was high enough, about 30 degrees above the horizon. Genzel makes the cautious remark in regards to Venus and Mars that these two planets, quote, may have been visible, unquote. However, this probability is low in what was practically broad daylight. All other hopes have been for Jupiter and Saturn, but it turned out that Jupiter was below the horizon during the eclipse and therefore invisible. And as for Saturn, although it was above the horizon, its location was in Libra, a long way off to the south. And according to Genzel, its visibility was very dubious. We have used the TurboSky software in order to compute the planet locations for the time of the eclipse that occurred on 3 August 431. What one sees here, it's in figures 2.8. So, yeah, this graph here, 2.8. What one sees here is a view of the sky from Athens for the maximal phase of the eclipse at 14:57 or 2:57 p.m., and it would be Greenwich Mean Time. It is clear that Venus, Mars, and the much dimmer Mercury are close to the Sun and thus rendered invisible by the rays of the partially obscured radiant orb. Their visibility in broad daylight is extremely improbable. The gravity of the situation that the proponents of Scaligean chronology had been well aware of made Johnson suggest a different eclipse, one that occurred on the 30th of March in 433 BC. However, it isn't included in any triad. The nearest triads are 447, 441, and 430 BC, and 412, 405, and 394 BC. They don't fit for different reasons. The phase value of the eclipse suggested by Johnson also turned out to have equaled a mere 7-inch 8, which is even less than the eclipse mistakenly suggested by Petavius. Stockwell then tried to revise the calculations in order to make the phase maximal. However, the very peak of his ingenuity only allowed him the result of 11.06. However, Genzel's reaction to Stockwell's calculations was quite skeptical. Seyfarth put forward a hypothesis that Thucydides may have been referring to the eclipse of the 27th of January, 430 BC. However, despite the fact that the eclipse is far from fitting the description given by Thucydides, for instance, it cannot be included into any triad at all. A thorough check showed that the eclipse could not have been visible near Athens. Does it strike anyone else as strange that all of these guys are working like crazy to try to fit an eclipse, the one that's described by either Thucydides or the dubious author claiming to be Thucydides? They're working like crazy to try to make this stuff fit, instead of using a little scientific sense looking at it and saying, gosh, man after man after man has tried to reconcile all this with Scaliger Petavius, and they can't. Maybe there's something wrong with Scaliger Petavius. Maybe there's something wrong with this account by the so-called Thucydides. Maybe there's something wrong with all of it, because none of it can fit. All the king's horses and all the king's men could not put back together Thucydides' triad again. The shock of Ginzel mentioned eventually became replaced by a confusion of sorts, go figure, which had brought about altogether different considerations that led farther and farther away from astronomy, among those pure demagogy. Zech, for instance, tried to eliminate the problem by his reference to, quote, the clear skies of Athens and the sharp eyes of the ancients. The sharp eyes. Apparently different than our eyes. We must be digressing. Apparently, our contemporaries would fail to see any stars at all. But the ancients were an altogether different race. Their vision was a lot keener. They ran faster, too. He's got such a good sense of humor. Can't you at least appreciate his sense of... I do. I think he's very funny sometimes. Hoffman went even, which is funny because every time you see a picture of Fomenko, he seems to be like scowling, a very, very serious Russian scowl. But he's pretty funny. Hoffman went even further in his suggestion to consider the stars of Thucydides a mere rhetorical embellishment. This translates as, quote, we trust him in every other respect, but refuse to do so in this particular instance, unquote. Hoffman tries to find linguistic proof for his theory, implying that Thucydides reports the appearance of stars when the sun had already assumed the shape of a crescent. We have asked the philologist E.V. Alexeyeva, Department of Philology, MSU, 1976, to perform a philological analysis of the text that can be seen in Figures 2.3. The linguistic verdict was that the following four events are described by Thucydides. 1. The occultation of the sun. 2. The crescent shape assumed by the sun. 3. The appearance of stars. 4. The restoration of the entirety of the solar disk. Thus, the entire eclipse process is described. The darkening of the disk at the beginning, its transformation into a crescent, and the subsequent visibility of the stars. This only happens at the maximal phase of a total eclipse, and the return of the disk to its original form. The consequence of events 1 through 4 is quite natural, and is unequivocally defined by the grammatical structure of the phrase. Actually, that was exactly the way that the professional translator quoted above, F.G. Mashenko, translated this fragment from the ancient Greek in the 19th century. The analysis performed by E.V. Alexeyeva confirmed the correctness of the classical translation yet again. It wouldn't have been questioned in the first place if it hadn't been for the problem with astronomical dating that arose in this respect. Therefore, Hoffman's opinion, that was also shared by the modern astronomer Robert Newton, is really based on the wish to save Scaligerian chronology at any cost, and not the actual translation. We see that the attempt to substitute astronomy for linguistics does not solve the problem. Despite all this, the erroneous date offered by Petavius wasn't altered, and any modern history textbook indicates the date that the Peloponnesian War began as 431 BC, albeit for no other reasons than Petavius's opinion. His chronology has been legitimized despite its blatant deviation from the clear and unambiguous description of Thucydides. The description contained in the original text is detailed and fundamental, which makes all attempts of rectifying the case by playing with the text look ridiculous. Apart from Hoffman's in quotes solution, it was proposed to alter the durations of the intervals between the neighboring eclipses, the ones that equal 7 and 11 years according to Thucydides. However, even the authors of this proposal refused to elaborate on it. It is hard to doubt that Thucydides was referring to a full eclipse when describing the first one of the triad. In case of the second eclipse, which was partial, he explicitly states that, quote, a partial eclipse of the sun occurred when the moon was new. The word partial is used here. Apparently, the author understood the difference between a total eclipse and a partial eclipse quite well. That is why he emphasized the visibility of the stars in the first case, which is a hallmark of a total eclipse. Let us give a summary. The astronomers failed to find any other fitting astronomical solutions in the interval between 600 and 200 BC. However, no one had thought of broadening the search interval so that the Middle Ages would be included. It is well understood that they all have been raised on Scaligian chronology and trusted it by and large. As a result, the erroneous triad of Petavius was kept, despite the fact that this solution, in quotes, contradicts the text of Thucydides. The use of the independent dating method in the entire interval between 900 BC and 1700 AD shows that a precise astronomical solution does exist. Furthermore, there are only two solutions that fit exactly. The first one was discovered by N.A. Morozov, and he gives that same reference, 544. The second by A.T. Fomenko during a new analysis of the ancient and medieval eclipses. The first solution, N.A. Morozov, is that 1133 A.D., 2 August, total solar. 1140 A.D., 20 March, total solar. 1151 A.D., 28th August, lunar. The second solution by A.T. Fomenko was 1039 A.D., 22 August, total solar. 1046 A.D., 9th April, partial solar, and 1057 A.D., 15th of September, lunar. Even condition 12, stipulating the time around March for the second eclipse, is met here. More importantly, the first eclipse is total, the way Thucydides describes it. Thus, once we manage to venture outside Procrustean paradigm of Scaligian chronology, we found the answer to a question that has been of great interest to astronomers, that of the astronomical descriptions contained in the Book of Thucydides. Taking all the facts that we already know into consideration, we should conclude that the solution closest to historical reality is apparently the one suggested by Morozov, the more recent triad of eclipses falling on the middle of the 7th century, namely 2 August 1133 AD, 20 March 1140 AD, and 28 August 1151 AD. The 11th century solution is most probably too early. Morozov's 1133, 1140, and 1151 AD solution is illustrated in Figure 2.9. One can see the lunar shadow tracks on the surface of the Earth for total solar eclipses of 1133 and 1140, as well as the zenith visibility point for the lunar eclipse of 1151 AD. We have verified the two solutions listed above with the Turbo Sky software. Let us quote the exact data characterizing the total eclipses of 22 August 1039 and the 2 August 1133. They are listed as full in the Appolzer eclipse canon. The TurboSky application identifies them as total eclipses as well. We shall give the geographical coordinates of the beginning, middle, and end of the lunar shadow trajectory on the surface of the Earth for the total eclipse of the 2nd of August, 1133. The first line gives the longitude and the second the latitude. So he gives these three numbers. See where they are. Okay. Which the first three is -89, +8, and +72. The second are +52, +53, and +9. The umbral lunar shadow had been at the central point of the trajectory with the sun in the zenith from about 11:15 to 11:17 Greenwich Mean Time, according to the TurboSky application. For the eclipse dating from 22 August 1039 of the second triad, which would be the 11th century one, the umbral shadow of the moon was at the central point of the trajectory at about 11:15 Greenwich Mean Time. The coordinates are 7 degrees of eastern longitude and 45 degrees of northern latitude from TurboSky. N.A. Morozov made the following justified remark regarding the full eclipse of 2 August 1133 in the 12th century triad. Quote, "The sun appeared to rise in total occultation on the southern coast of the Hudson Bay. It had been matutinal in England as well, came to Holland at noon, to Germany, Austria, the vicinity of the Bosphorus, Mesopotamia, and the Gulf of Arabia, and set in complete darkness in the Indian Ocean. The eclipse was full and its phase maximal. Everything went dark, and one could naturally see the stars in the sky." Thus, the 12th century triad discovered by N.A. Morozov can be seen as follows. 1. The first total eclipse of the sun occurred on 2 August 1133 A.D. and happened in the following manner. And he gives the three numbers, -89, +8, +72, and the next three, +52, +53, +9. The central point of the lunar shadow trajectory on the surface of the Earth was passed between about 11:15 and 11:17 Greenwich Mean Time. The second full eclipse happened on 20th of March 1140 as follows. So you got -96, -30, +48, and then +20, +42, +55. The central point of the lunar shadow trajectory on the surface of the Earth passed at approximately 1340 Greenwich Mean Time. 3. The partial lunar eclipse of 28th of August 1151 AD had the maximal phase value of 4 at 2325 Greenwich Mean Time. The zenith visibility of the moon concurred with the point whose geographical coordinates were 8 degrees of eastern longitude and 7 degrees of southern latitude. This 7th century triad is ideal in all respects. The second eclipse really occurred in March, as one should have expected from the text of Thucydides. The 11th century triad discovered by A.T. Fomenko. 1. The first solar eclipse of 22 August 1039 AD happened in the following way. And then he gives the figures again, which I'm not going to read because you can go and check this at archive.org. And I don't think me just reading it is actually providing far more clarity to those listening. Anyways, these are sets of figures concerning eclipses. Anyways, he says the central point of the lunar shadow trajectory on the surface of the Earth was passed at about 11:15 Greenwich Mean Time. The second solar eclipse, partial, of 9th of April 1046 occurred as follows, and he gives those numbers. The central point of the lunar shadow trajectory on the Earth's surface was passed about 5:46 Greenwich Mean Time. The partial lunar eclipse of 15th of September 1057 AD had the maximal phase value of 5 at 1809 Greenwich Mean Time. The zenith visibility of the moon concurred with the point whose geographical coordinates were 86 degrees of eastern longitude and 1 degree of southern latitude. The Thucydides eclipse triad is a very substantial argument proving that the history of the Peloponnesian War by Thucydides couldn't have been written earlier than the 11th century A.D. It is most improbable that the triad is a fantasy of the author, since in that case a fitting astronomical solution would most probably have been non-existent. It is also hard to consider the eclipses an apocryphal part of the ancient text, since they fit the consecutive and detailed narration incredibly well. N.A. Morozov appears to have been correct in noting that, quote, the Book of Thucydides isn't ancient or medieval. It dates from the 13th century of our era at least, the Renaissance epoch. You get that? I'm going to take a moment to reflect here, and I want you to reflect what he's saying about these eclipses and when this eclipse triad could have occurred. I find it to be quite astounding. I mean, it hurts my brain, not in the sense that trying to understand what he's saying about these eclipses or the way and where they could have been viewed and how. Now, I don't pretend to be the mathematician that can look at all of these figures that he's giving and easily say, oh yeah, definitely, I can see by the numbers, for sure, right on the money. But I am following the logic of what he's saying. And when you do that, it's pretty strange that ecliptic triad couldn't have happened until what we would consider somewhere around the 10th to 12th century. Maybe later. Definitely a lot of heavy stuff to think about. Section 2.4. The eclipses described by the ancient Titus Livy. Let us give a few more examples, omitting the details this time. We shall just report that the eclipse from the History by Titus Livy, that the modern chronologers ascribe to 190 BC or 188 BC, also fails to satisfy the description of Titus Livy. The situation with the eclipses of Thucydides is repeated yet again. It turns out that an independent astronomical dating yields just one precise solution in the interval between 900 BC and 1600 AD, and that would be 967 AD. The situation with the lunar eclipse that Titus Livy describes in his History is exactly the same. Scaligerite chronologers suggest that Livy is referring to the eclipse of 168 BC. However, analysis shows that the characteristics of this eclipse do not fit the description given by Livy. The eclipse that he describes could really have happened on one of the following dates. Either in 415 AD at night between the 4th and 5th of September, 2. in 955 AD at night between the 4th and 5th of September, or in 1020 AD at night between the 4th and 5th of September. This pattern of false dating goes on and on. A list of such examples includes all the ancient eclipses that have detailed descriptions. We shall present the whole picture of this effect of moving ancient eclipse dates forward in time below. And I'm at an hour and 18 minutes. And let's see, the next section is 3, transferring the dates of the ancient eclipses forward in time into the Middle Ages eliminates the enigmatic behavior of the parameter d. That's quite interesting. I'm just moving ahead a little bit to see how long these sections are. Section 4 is extremely long. Well, longer than I think I have time for, but section 3 is not even a half a page, so I will read section 3. And that is, the transferring the dates of the ancient eclipses forward in time into the Middle Ages eliminates the enigmatic behavior of parameter D. The author of the current book proceeded to recalculate the parameter D values using the new dates for ancient eclipses that were produced as a result of the method described above. The discovered effect of moving ancient eclipses forward in time led to the identification of many ancient eclipses with the medieval ones. This, in turn, allowed us to expand and alter the list of such medieval eclipses. New data were obtained from the descriptions considered ancient earlier on and added to the medieval eclipse descriptions. Nevertheless, research has shown that previous values of D basically didn't change over the interval of 500 to 1990 AD. A new curve for D can be seen in figure 2.10. And let's see. I'm just going to go ahead so that they're on the page. There it is right there. There's these two figures. The new curve is qualitatively different from the previous one. In the interval between 1000 and 1900 AD, parameter D reflects in an even curve on the graph, one that is practically horizontal and fluctuates around a single constant value. It turns out there have never been any drastic leaps in the parameter, whose value has always equaled the current. Therefore, one doesn't have to invent any mysterious non-gravitational theories. The fluctuation of D values, which is rather low in the interval of 1000 to 1900 AD, grows significantly when we move from 1000 AD to the left towards 500 AD. This means that either the scarce astronomical descriptions that chronologists ascribe to this period are very nebulous, or more likely, these chronicles are also misdated, and the events that they described are in need of redating. However, due to the utter vagueness of the remaining astronomical descriptions, they cannot be used for dating purposes since they offer too many solutions. The redating of the events that precede the 11th century shall have to be done by other means and methods, some of which shall be related below. Further on to the left from 500 AD, we see the zone of no observation data. We know nothing at all about this epoch. The resulting picture reflects the natural temporal distribution of the observation data. The initial precision of the medieval observations of the 9th through 11th centuries was naturally rather low, and then grew together with the precision and perfection of the observation techniques, which resulted in a gradual decrease in the fluctuation of D values. Now, very interesting. I'm looking at these two graphs. I'm going to zoom in on them. Hopefully I didn't zoom too much. And I can't fit both of them in the page without, I'd have to zoom out. And he's showing that the upper graph was R. Newton with this whole D parameter, and then the lower was A.T. Fomenko. And he says below these two graphs, Figure 210, comparison of D graphs is calculated by R. Newton and A.T. Fomenko. Parameter D is measured here as seconds divided by century squared. The new D graph has neither gaps nor leaps and fluctuates around a constant value. All right, so since I'm at the end of section 3, and we'll be moving into 4 next time, I want to try to offer what I don't believe is brilliance in any way. I suppose if an astronomer had actually been reading this and interpreting it, it would be far easier to understand than myself. But based on everything he's saying here, and everything that he's described with R. Newton's great fluctuation of this parameter d with the moon and eclipses, and how it just seems to me that because all of these other so-called scientists are just trying like crazy to make Scaliger chronology work. They are trying against logic, against science, against truth, honesty, and sincerity to make the Scaliger chronology seem realistic. Then when you consider who R. Newton's employers are, and that his employers have been exposed as nothing but liars, fakers of information, falsifiers of data, have been caught in lie after lie after lie. It has been shown that so many of the founding members of NASA and all of their astronomical predecessors, which led to the development, who laid the groundwork of thought and ideology to allow for the development of something like NASA, and all of their 20th century cohorts being either provable witches and occultists, or just plain, and I don't mean to demean it any, because I find these people and their practices just as dark and dubious, Freemasons. So, who are we to believe? Are we to believe chronologers like Scaliger and Petavius, who, concerning what exists that we common people can find, concerning the lives of and the characters of men like Scaliger and Petavius, to be of the worst sort, the most dishonest? And when their chronology is concurred with by folks like Kepler, who also have immensely questionable characters and credentials, all the way up to a NASA employee like R. Newton, who is basically just going to pull this theory of the moon's odd behavior out of his butt. Or are we to at least give some credit to Morozov and Fomenko for correctly, or trying to, come very close to being correct in calculating the parameters of an ecliptical triad written about by this Thucydides. Was Thucydides a real historical character? If he was he the one who wrote these chronicles of Thucydides and the Peloponnesian War? And if so, we can obviously see that his eclipse triad does not fit the time given. So much to think about. Until next time, I may put a gap of a couple of days in between because of that, because this was extremely heavy, dense material, as has been par for the course thus far. And really, as I look ahead, a lot of this is going to be more astronomical observations and the zodiac. And the funny thing is about the bodies in heaven, the sun, the moon, the stars, the wandering stars or planets, they are meant to be, or whether you want to argue over what they were meant to be, they can certainly be used as a timepiece. So no matter how much we understand or don't understand about the way that the heavenly bodies are watched and have always been watched by timekeepers and historians, we should be very willing and open-minded and wanting to learn about how these calculations work, because it does seem to me that that great big clock in the sky is very, very accurate and does not lie like, say, certain chronologists and so-called scientists that I don't even have to mention. So until next time, everybody, take care.